Hi everyone, my name is Gulden Othman. I'm a postdoc at the University of Hamburg. And today I will tell you the status of the ALPS II experiment on behalf of the ALPS II collaboration. So first, since you are not hearing a lot about light shining through walls experiments at this conference, I want to give you motivation for light shining through walls experiments. So first of all, we know at this conference that we have extensive observational evidence for the existence of dark matter. And axion-like particles are a good dark matter candidate as well. Light shining through walls experiments are nice because we can search for axion-like particles in a model-independent way. That also allows us to test astrophysical observations like stellar cooling and the TeV transparency of the universe. So just to remind you, a lot of experiments that we're seeing at this conference, and we will see, take advantage of the axion or axion-like particle coupling to photons. You can look, for example, at the decay of an axion-like particle to photons. This is what's done typically in astrophysics and cosmological surges. There's also this TeV effect, where an axion can convert into a photon in the presence of an external magnetic field. This is done in haloscope and helioscope experiments. And in the inverse process, you can have a photon, where in the presence of a strong external magnetic field, converts to an axion-like particle. And light shining through walls experiments take advantage of both of these effects. So what we do in the light shining through wall experiment, we have an incoming source of photons that goes through an applied external magnetic field. The photon may, in this magnetic field, convert into an axion-like particle, which can traverse an opaque barrier and reconvert into a photon in the presence of an external magnetic field on the opposite side of the wall. And the reconverted photon would have the same properties of the initial photon, which is something very important here. So the figure of merit for these kinds of searches are the conversion probability from photon to axion-like particle to photon. That's given by GA gamma times the magnetic field strength times the magnetic field length to the fourth power. Now what we actually measure in the end is the reconverted photon, and the number of reconverted photons that we expect to get out. This type of experiment is also related to the magnetic field length strength, GA gamma to the fourth power, also on the power of the incoming light source and the energy and the measurement time. So one really important thing is without any enhancement, with magnetic field strength and length and laser power similar to the design of ALPS II experiments, if we wanted to reach GA gamma 2 times 10 to the minus 11 inverse GeV, we would see one photon every 150,000 years. I don't know about you, but my postdoc contract doesn't last that long, unfortunately. So we need to find a way to enhance this. And this is exactly what we do in the Any Light Particle Search 2, or ALPS II experiment. So ALPS is located at DAISY in Hamburg. We are 6 institutions with about 30 members across Germany, the US, and the UK. So what we do in ALPS to search for axion-like particles is light shining through wall experiment. And we use mirrors in the production region and the regeneration region to enhance our signal by factors beta P and beta R respectively, which I'll talk about in just a second. So I want to go through here. This is the number of expected photons that we would expect to see at the detector, and tell you the different parameters that we will see in the ALPS II experiment. So first, start with the laser. We have a 30-watt, 1064 nanometer laser. This corresponds to about 1.165 electron volts. Then we use 24 straight Hera magnets, 12 in the production region and 12 in the regeneration region, for a length about 100 meters each. And the magnetic field strength is 5.3 Tesla. We use Fabry-Perot resonators, which are very high-quality mirrors, in the production and the regeneration region. And this is where these beta factors come in that I told you about. This is how we get an enhanced signal. So this is how we can actually perform an experiment in a reasonable amount of time. So for the production cavity, we expect a factor of 5,000 increase in power. So this means we would have an input of effectively 150 kilowatts of power. And in the regeneration region, maybe we should get up to an enhancement of up to 40,000. Now this would translate into a regenerated photon power of 10 to the minus 24 watts, which would correspond to 1 photon per day for GA gamma 2 times 10 to the minus 11 inverse GeV, which is a much more reasonable figure, fully. Now, this is still a fairly low number, so we have to have sensitive detectors to be able to reach our desired sensitivity for ALPS II. And we have two separate detectors. The first that we'll use is a heterodyne sensing technique. So this is similar to what is used in the LIGO experiment, for example, where you have you mix a weak signal with a frequency-shifted local oscillator to create a beat note signal. And the important thing here, without getting into too many details, is if you do perform something called an IQ demodulation at the right frequency, after measuring long enough, this is your expected noise floor here, and the blue would be a signal demodulated at the right signal, or at the right frequency. If you measure for a long enough integration time, then your signal would overcome the background, and you would be able to detect something. And so we have demonstrated, the group at the University of Florida, 10 to minus 24 watt sensitivity with the heterodyne sensing technique. And if you're interested in reading more about this, there's a paper explaining it, reference here. So again, the heterodyne sensing technique will be the first detector that we use for ALPS II. Now, since we are the only light shining through wall experiment that laboratory-based that's sensitive at this sensitivity, we need two different detection techniques that are independent of each other in case we do find a detection to cross-check each other. So in addition to looking at the power, like we do with heterodyne sensing, we can do photon counting using transition edge sensors. Now you've heard about these devices at a couple of other talks. A lot of them are using transition edge sensors effectively as very sensitive thermometers, where they are attached to some other kind of substrate. So they are not really the bulk material, they're just kind of the main readout. What we're actually doing with ALPS II is we're going to use a transition edge sensor as a detector itself. So it's not mounted on anything else. And what we have here again, as was mentioned previously, we have a superconducting material that's near its transition edge. So an incoming 1064 nanometer reconverted photon would heat up this material. That would cause a small change in resistance, which results in a small change in current, which is then measured with squid electronics and read out as a change in voltage over time. Now, an also important fact, the integral of this change in voltage over time is proportional to the particle energy, which also allows us to have some more discrimination against different photon energies. So we can discriminate better between signal and background. We've demonstrated low dark count rates with this detector when there's no optical fiber attached. And you can see there was a poster yesterday by Manuel Meyer, which I believe is probably still up, that talks about machine learning to reduce the backgrounds that we see in our transition edge sensor. And also Rick Upshaw has a poster talking about how the tests will be integrated with the ALPS II experiment. Now with all of these factors, our design sensitivity for ALPS II is 2 times 10 to the minus 11 inverse GeV for an axion-like particle mass of less than 0.1 millielectron volts. Now, this is an increase in sensitivity of greater than 3 orders of magnitude over previous light shining through wall experiments, Oscar and ALPS I, for example, and also a factor of 3 improvement over PAST, which is also in this same region as light shining through walls experiments. So this is really exciting because we also will begin to probe astrophysical phenomena, you see here, in a model-independent way. And I mentioned again, stellar cooling and TeV transparency. Most exciting is we will have an early science run with limited sensitivity later this year. So now going into a little bit more of the status of the experiment. So we have a high-powered laser that's an amplified non-planar ring oscillator. We've demonstrated over 60 watts of power at our wavelength 1064 nanometers and greater than 90% power in the fundamental mode. I mentioned before, we used 24 Hera dipole magnets, and all of these magnets were installed and aligned in October 2020. And then in March this year, we successfully ran the magnet string at full current, which means 5.7 kiloamps to achieve 5.3 Tesla. And we also demonstrated, for example, our quench protection. Something that's really exciting is with our regeneration cavity. I'll remind you, the regeneration cavity is on the other side of the wall where the photons, where the axion could reconvert to photons. We have demonstrated the longest storage time of any Fabry-Perot cavity ever, which is really exciting. So that means we've stored light in this region for 6.7 milliseconds. And that would correspond to a power buildup factor of about 7,000. So this is world leading at this time. And there is more information about this, such a talk by Aaron Spector at IBM that was a couple weeks ago. His slides are on Indico if you're interested in reading more about the optical setup specifically. So our first science run will be before the end of this year. And what we'll be doing is operating similar to what I showed before, but we will be operating without the fabric-row resonators in the production cavity. So we're commissioning without the production cavity, and this allows us to have a simpler control scheme, also stronger signals for stray light hunting. And we will be operating with an input laser power of 50 watts, and we will have our regeneration cavity in place with a improvement factor of 10,000. So this is, overall, will give us a factor of about 350 improvement over the ALPS I sensitivity. So we hope to reach GA gamma 2 times 10 to the minus 10 inverse GeV. So just to give you an idea of the schedule for ALPS II, before the end of this year, we will have our first early science run that I just mentioned, and we hope to reach there a sensitivity of 2 times 10 to the minus 10 inverse GeV. Then, in the first half of next year, we will be commissioning our full optical system with the production cavity, and then have a science run in summer 2023 with the full optical system, where we hope to reach 3 times 10 to the minus 11 inverse GeV. For the second half of 2023, we will be doing commissioning with upgraded optics. And then we will do our science run with the full sensitivity that we hope to reach with ALPS II, which is 2 times 10 to the minus 11 inverse GeV. So in 2024, we will remove the heterodyne sensor, and we will begin commissioning the optical system for the transition edge sensor, so that we can, maybe if we're really lucky, we see a discovery, and we can reconfirm it with the transition edge sensor. And then we hope to have a science run with transition edge sensor at the same sensitivity, 2 times 10 to the minus 11 inverse GeV by fall 2024. So just to give you a quick summary, ALPS II is a light shining through wall experiment that will improve the limits of GA gamma by over 3 orders of magnitude over Oscar and ALPS I. And this is really exciting, again, because we'll be able to begin checking astrophysical observations in a model-independent way. Our first science run will be before the end of the year, where we hope to reach sensitivity GA gamma 2 times 10 to the minus 10 inverse GeV. And our full sensitivity run after upgrades will happen hopefully around fall 2023, where we will reach another order of magnitude improvement, 2 times 10 to the minus 11 inverse GeV. So I think I finished a little bit early, so hopefully everyone has time to ask lots of questions.
Thank you for updating us on this exciting stuff. Question?
Hi, thank you for this very nice talk. On slide 13, you showed the power factors for the regeneration and production parameters.
Yes.
And they are different. Can you comment why?
I think this is related to, sorry. So I'm not really an expert with the optical system. I'll preface that saying I work on the transition edge sensor. But I think this has to do with the mirrors that we have in the production and the regeneration region. And also probably the fact that you have, on this side, you have to deal with a high-powered laser. So the high-powered laser can further degrade the mirrors on this side. So I think that makes it difficult you can damage the mirrors before you're able to reach such a high enhancement factor. And on this side, we have really no input laser. So we're just amplifying very, very small signals. So we can increase it much more than, does that make sense?
Thanks.
Question over here. Wait. We're going to take this one first.
Actually, my question was almost the same. And I would make the two cavities the same, 40,000. This way you would use less powerful laser. So what's the idea?
Yeah. So
Yeah,
so the important factor here is is this power buildup. So this is the important factor here. So what matters is your laser power times your amplification here. So if you increase one and decrease the other one, you're kind of getting the same result.
Thanks for the really nice talk. One question and one comment perhaps. So my question is there some way to modify the scheme of this kind of experiment so that one doesn't run into a wall when one comes? run into a wall.
Metaphorical wall? Or?
Apologies, sorry for that. If anyone wants to go below 10 to the minus 12 in terms of the constant. Presumably you can't have this kind of linear thing on and on or much larger than U graph kind of constant or something. So is there some modification of a light shining through wall experiment where you don't need longer and longer kind of sort of cavities and still can go beyond ALPS II?
So there are, so I think there are kind of a lot of things within this question. So you mentioned, yes, we can definitely, you can see here, the main ways to improve are to increase your magnetic field strength. Right now we have 5.3 Tesla, which is really not that much. There are magnets that are much stronger than this available now and that have also higher aperture. Okay, I'll keep talking. So we're limited because we're using magnets from Hera. So we had to take these magnets that were curved and straighten them, and that limits our aperture. So we can have more magnets that are with higher aperture and more magnetic field strength. That would be good, and also increase the length of our setup. Other things are related to optics, for example, but there are other designs that for light shining through walls experiments that are not based on optical light. So, for example, you saw a talk yesterday about using gyrotron with fabric pearl cavities to search for axions and axion-like particles. This is kind of one way to improve things further. But yeah, there are several proposals, or there are at least two proposals for improving light shining through walls. One is based on basically improving ALPS, and one is based on going to millimeter wave sources.
Thanks. And you said that this can be used to check the astrophysical observations. Maybe you mean that it can be used to check the astrophysical or the ALP interpretation of astrophysical observations.
Okay, so I'm not an astrophysicist, so maybe I'm not saying things in the right terminology. What I mean is that in astrophysics you have model independence, or you have model dependence, and yeah, so we can reach the same sensitivities and probe the same sensitivities in a way that is model independent, so that we're being complementary to each other.
Yeah, thanks.
Question over here.
Maybe you said this, and really excellent talk. Maybe you said this, I missed it, but do you have a thought of also dark photon?
I don't have that, but we can do the same thing, turn off the magnets and do a dark photon search as well.
And this is also a plan?
It's not a part of the main plan because it takes time, but most likely if we finish for example, we finish the PET run, we can do a dark photon run at the end, and then if we finish the test run, do another dark photon search. But our main goal is actually looking for axions and axion-like particles, so we want our magnetic field.
Okay, so exciting time. So you have a slide for transition-less sensors. And then in the bottom of the slide, you said the dot counter rate is 10 to the minus 6 or something?
Yes.
So this is fairly low for me, as an action experiment. So is that the typical value for test in the community? Or do you have any inspiration why the dot count is so low?
So this is actually, I would say, high compared to other setups that we've seen. For example, if you look, our transition edge sensor comes from NIST, and we have our squid electronics from PTB. Similar setups from NIST and PTB have shown comparable or lower dark count rates, actually. So this is I would say these are kind of the cutting edge transition edge sensors, cutting edge. So this is reasonable, and we actually, but the caveat is that when we do plug in an optical fiber, like we will for tests, or for when we run with ALPS, we see higher dark count rates from, for example, black body radiation coupling into the fiber and reaching our sensor. So there are other ways that we have to mitigate, other backgrounds we have to mitigate. This is just pure dark counts from the sensor operating by itself.
Thanks for the talk. Two questions. One, it would seem that we actually don't need to turn the magnets off to look at our photon. We can look at other
Yeah, I guess we don't need the magnets, but
yes.
Waste of energy, maybe.
The other question is, maybe I misunderstood something, but Is your line width in the regeneration cavity narrower than in the production cavity?
Here? No. So what is drawn here in this cartoon is representing, what we have to do is keep these cavities mode matched. So this involves keeping them mode matched both in frequency domain and in spatial domain. So essentially, if you don't keep them matched, so this is kind of showing like this shape is continued on in here. And that means that otherwise, this factor of 5,000 wouldn't really couple to this factor of 40,000 in the end. You would, if you were in a different spatial mode, then you would lose all the enhancement that you got in your regeneration cavity and have to start over again. So something that we have to be really careful about is keeping these cavities mode matched. And we have some optical techniques that we do to keep this.
So if you don't spoil the regeneration cavity to have the same width as the production cavity, right, you are going to lose?
Can you repeat that?
Okay, maybe we can get this.
No, I mean, what it means is that you have smaller line width in the right cavity than in the left cavity, right? The line width of it, I mean, it's like, if they have the same length, that is the free spectral range, and then you have
I think maybe Axel wants to answer this because I think maybe I don't know what line width means.
Axel, you're not to hear you.
I thought you were asking about how we are, keeping them matched. But.
So both cavities are locked to a frequency standard and they are not fluctuating within the bandwidth.
Yes.
So both are locked to a frequency within. So the production cavity is controlled much more closely to the frequency standard than allowed by the bandwidth. And therefore we make sure that the production cavity always is at a frequency which is within the line width of the regeneration.
I think I didn't understand what line width meant.
This is the idea.
Yeah.
It's kind of locked in.
Thanks.
Okay, I think probably. Well, thanks again, everyone.
Let's make her speaker.